Okay? So what happens if we say switch to an SN2? Why is the one on top reacting faster? Which is a really weird statement to make, by the way. Why is looking at the one on top going to be a really weird statement to make for the SN2? So why is it but I said weird. Why is it a weird statement to make? It's a carbocation, and SN2 reactions don't make carbocations. So comparing those structures under an SN2 reaction is a horrible idea because those structures don't exist under SN2 reactions. So what happens if we switch it up? So let's take a look at the following according to SN1, the top one. Should that react according to an SN1 mechanism? No. Okay. Here and a no. How about the next one down?
Yes.
Shh. Next one down.
Yeah.
So I heard a yes on that one, so we're going to stick with that. Okay? And because we're going to stick with that, here's why we're going to stick with that. Why is one no and the third one yes for SN1? Are those not exactly the same?
So one of them is right.
So one of them is correct. That is true. Okay? So why did we say no on the first one? For those of you that said no, why were you saying no?
Because most likely it does SN2 more than SN1.
Saying it does SN2 isn't a valid answer for why this doesn't go SN1. Okay, that still doesn't address SN1. Okay? Why is this not an SN1 reaction?
Because the carbocation.
We have to decide which mechanism we do, we have to look at the reasoning behind it. SN2, yes, small backside attack. Sure, fine. That doesn't address the SN1. The SN1 needs to evaluate the stability of the carbocation. Can I form a stable carbocation? What happens if I erase that bromine? Come on. I would have a primary carbocation, and that's why you're telling me no. Right? Okay. Shh. Look at the bottom one. The bottom one you said yes on. Top one you said no, and if we erase the bromine, what kind of carbocation do we have? Primary again. So again, we're having an issue here. Okay? Why is the bottom one saying yes and the top one saying no? Because interestingly enough, the people that said yes for the bottom one are still saying no for the top one. That's a bit of a problem. What is special about both those structures? They both have resonance. I can take those electrons and move them over. What does that mean happens to the carbocation? It becomes stable. And if I evaluate the reactivity of the carbon in both those structures, okay, to evaluate our reactivity, we need to look at charge. So the charge in the leftmost structure on that carbon is what? +1. The charge in the rightmost structure is? Neutral. Okay, we're looking at the carbon that was reactive. We're not looking at the whole molecule, we're looking at that reactive position. That charge is now spread across how many structures? 2. Which means the official charge, or the unofficial charge on that carbon is +0.5. What is the official charge on the carbon in the tertiary structure? It's just 1. It's +1, period. Okay? There's no other structures to represent it. That charge is +1. Which is more stable? The primary one in the top or the tertiary at the bottom? Why the primary one more stable? It has less of a charge. It's closer to being neutral. There's a resonance effect. That resonance effect trumps our primary, secondary, tertiary rankings. Okay? A primary structure with resonance is more stable than a tertiary structure without resonance. So when we think about our SN1 reactions, we should not be thinking just primary, secondary, tertiary. What we need to be thinking is the stability of the carbocation. Yes, tertiary is more stable than secondary, more stable than primary, more stable than zeroary. But there's other things that can stabilize a carbocation. like resonance. Make sense? So that top one, should it react according to an SN1? Yes. The no answer was premature. You saw the primary substrate and said primary wasn't stable. Resonance can stabilize that carbocation. The bottom one, also a primary substrate, but what happens there? We have resonance outwards. Okay? Those two characteristics, or those two types of structures, or that position is now has such a different chemistry associated with it that we give it a different name. So the top one, that position where the bromine is located, is known as the allylic position. And the bottom structure, that is darn similar to the same position, except it's not next to just a pi bond, it's next to a benzene ring. So we come up with a new name for that. It's referred to as benzylic. Okay? Chemistry is ultimately the same. We have resonance to stabilize that. Okay? What happens in the middle structure? So now everybody's saying, well, it should have been a no. Hindsight's 20/20. What has to happen in the SN1? We have to form a carbocation. Why is that carbocation not stable? There's a myriad of examples. One thing we could look at is resonance. And when you look at resonance, that would suggest that it should form, not that it shouldn't form. So already we've got a problem there. Okay? So let's take a look at said resonance. Let's move those pi electrons there. Can we do that? No. It's actually going to be physically impossible for multiple reasons. One, that means the structure there has to bend out at 180 degrees. Not going to happen, okay, because it's locked in the ring. Take it for a second loop. Where is the positive charge found? In what orbital? A p orbital, which is why we can typically do resonance. Okay? Where is that p orbital with respect to the p orbitals within the ring? Wait, what? Okay, so let's grab some pens. I'll do it on each side, and for those of you watching at home, top. Our double bond within the ring. Those are overlapping p orbitals. Where are those p orbitals in the ring? They're perpendicular to the plane of paper, so they're coming in and out of the board like this, all the way around, right? Yep. If I have a positive charge, I have another p orbital. It cannot be the p orbital occupied in the ring because, well, that was already there. That was already in the ring. Which means where is that new p orbital? Perpendicular to the system. Okay? Either on that axis or here. Can I take electrons and share them with that blue? Because perpendicular orbitals. It's not even out of phase. They're perpendicular to each other. I cannot do resonance because the orbitals do not overlap. Zero overlap means zero resonance. Okay, so that carbocation is not stabilized via resonance. Okay? The second, our secondary issues with that carbon, what is its hybridization? It's actually sp, which means even as drawn, it needs to be 180 degrees. Okay? Everything about that is screaming, this is horrible. Okay? Because it started, and then we can take it a step back, go all the way back to the beginning of it. What did it start as its hybridization? Now, Rebecca, you're right. sp2. What is different about the sp2 atom versus the sp3 in both the allylic and the benzylic? The sp2 atom is more electronegative, which means what is it doing to the electrons in that bond? Holding them tighter, making the bromine even more difficult to leave. Okay. That position gets its own special name, but because it's a ring, it gets a specialer name, and I don't have that name, so I'm just going to clean out the ring a little bit. And that position is now known as the vinylic position, not reactive in an SN1 mechanism. Okay? Clear it up. What happens if we make it? Nope, that didn't work like I thought it would. We've got a reactivity summary at the bottom. That reactivity summary is for which mechanism? SN1. The tertiary allylic is more stable than the secondary allylic, more stable than the primary allylic, which reacts faster than the tertiary, faster than the secondary. Notice, do you see zeroary or primary? Why not? They don't form. Okay, we cannot form the carbocation there. Okay, unfortunately, that's kind of a memorization thing. We don't have any other example other than that, just to say that, well, they're really unstable, nothing stabilizes them, and they're so unstable that they don't happen. Okay? What happens if we ignore that bottom part, and the left part, and that part, and that part, and change the question? Lots of stuff happened. Is the question now asking about SN1? No, what is it asking about? SN2. What happens in the SN2? Backside attack. Which of these will react? The first one should react. Second one? No. Bottom one? Yes, it is a primary substrate. Which one will react faster, top or bottom? Why the top? Doesn't have the ring. There's a little bit less sterics there. We can make a pretty solid argument that the top should react faster than the bottom due to a steric hindrance effect. The second one, why does that one not react? It's attached directly to the ring. Okay, so I want to draw another structure here, and Tristan will love this example. Won't you, Tristan? Good answer. Is that bromine attached to a ring? Does that one react in the SN2?
No.
Yes. Damn it. Fair enough. Okay. Structure on the right does not react. The structure on the left does react. So making the statement that it's attached to a ring is an invalid argument. That's not helping us.
Is it a ring with pi bonds?
What are you referencing when you're talking about a ring with pi bonds? Because this ring now has a pi bond. That's still going to react.
Pi bond, pi. It's a carbon. Oh, that carbon has its octet.
Structure on the left, our purple carbon, what is its hybridization? What is the hybridization on the right? sp2. Why is that changing things? What happens to, say, the geometry, Tristan? Structure on the left is tetrahedral. Structure on the right is planar. With it being a tetrahedral structure, I don't care if those two atoms are connected out to a ring, because it's the exact same as if I didn't have the ring. The backside is still accessible. What happens if I drop it into a planar situation? There. Ta-da! I have a pi bond chilling out there. What's in a pi bond? Electrons. What happens when the nucleophile gets near those electrons? It repels away. What happens? No reaction. Right? The reason why that second structure does not react has nothing to do with the ring per se. It has to do with the shape of that structure. You might say, well, why is that all that big of a deal? When we think SN1, we think carbocation. When you think SN2, you should think backside attack. There's another big common word. 2 words. Steric hindrance. And steric hindrance is just the electron repulsion. Where do we get electrons? Structure. Everything in an SN2 reaction is about structural repulsion. How do those pieces fit? You need to be aware of shape because you're looking at how they fit. Okay? In the SN1, we're caring less about how they fit because we're looking at the stability of the carbocation. The fit becomes a secondary object. Make sense? Okay. Leaving, sorry.
What if you were to add heat and then?
So heat is an extra caveat on this, because what does heat do? It breaks things. So heat can cause bonds to break that wouldn't ordinarily break. The issue with that is in the process of causing it to break, how can we then make? Becomes a little bit more challenging. The reason to make is we'd have to make something more stable. We wouldn't be making anything more stable here. Okay. So while heat can help push reactions, you still have to get somewhere that neutralizes your structure. Leaving group ability. If we were given this structure and I said, here's a strong nucleophile, it comes in and attacks that carbon. Zoop. Which group leaves? Right, how many groups could possibly leave? 4. 4 could possibly leave. Why did you eliminate one of those right out of the gate? Hydrogen is a horrible leaving group because it doesn't have any electrons. What would actually be leaving? Not hydrogen. Hydrogen with electrons. Hydride. Hydride is a horrible leaving group because of? Why is it not stable? Well, it's charged. And the next thing? Size. Hydrogen is as small as we can possibly get. Okay, hydrogen is effectively just lone electrons chilling. Electrons are not stable. Okay, so for size reason, hydride is a horrible leaving group. What other leaving groups do we potentially have? We have OH. Okay. Why is OH an issue? So a cheat is that we have a strong base. Strong bases are bad leaving groups because they are inherently reactive molecules. Okay? I don't want those leaving. So strong base, bad option. Next option. Chloride. Is chloride a better leaving group than all the others so far? Yeah. Why? Because it's big. It's going back to size. Chloride is very large, so it can stabilize that negative charge in comparison to the hydroxide, in comparison to the hydride. Right? Then what happens? We've got bromide, and bromide is even bigger, which makes it an even better leaving group. Okay? So ultimately, all we're trying to do is say what happens when the electrons leave with that atom. Is it stabilized? Okay? So traits of leaving groups, they tend to be electron withdrawing or very electronegative atoms because they need to take the electrons. Electronegativity mirrors that really well. They tend to be very weak bases. Right? Because if they were a strong base, what would they do? They would react immediately, which then means it's not leaving the structure, it's immediately coming right back on. Okay? We also tend to look at this extra fun word, polarizable, which is just a fancy way of saying it's really, really, really big. Okay? Your textbook goes through and lists out a whole bunch of leaving groups and ranks them all. Ultimately, you're just looking at that stability. Is it stable on its own? If it is, good for you. It's now a leaving group. Your chemistry can happen at that reactive site. Make sense? Okay. Solvent. Okay. Solvents very typically play a very kind of minor or hidden role. Okay. It's not really minor, it's one of the biggest roles that we have. Okay. If you tried to interact with anybody in the world right now, it becomes rather difficult because how would you interact with a person? Why is it easier to interact with me? You're in the same room. You're in the same, effectively, phase. So you can make that interaction relatively quickly. If you're in different phases, i.e. someone outside the room, you can't interact with them. The same thing's happening with our solvent. Our solvent tries to take those reagents, the nucleophile and our substrate, and bring them near each other. If they don't come near each other, they don't react. So the role of the solvent must be to dissolve both species. If it does not dissolve, multiple phases, reaction slows down, which officially comes out of 152. Okay? Our secondary kind of role behind this, and this is the one that's more important for us, is they can stabilize or destabilize our reagents or intermediates. Okay? And the first role to decide what's going on, we have to look at intermolecular forces. Are the intermolecular forces similar? Then they mix. Are they dissimilar? They don't mix. So we have polar and nonpolar for our solvents. What else do we have? Protic and aprotic. So 3 solvent classes. Every time we look at a mechanism, we want to decide what solvent's going to help this reaction out the best. Okay? So within our solvent classes, we've got polar protic, aprotic, and nonpolar. Let's take a look at those 3 solvents. I'll give you a minute. Classify them.
Non-polar and
Polar, aprotic, polar.
We're not getting very good record quality for people thinking at home while standing over there. Okay, all together on this side. First one is 3. All together on this side.
It's aprotic.
Acetic acid is 1, guys.
Oh wait, we're doing TSMO.
DMSO. That's a 2. It is not protic. Why is it not protic? For it to be a protic solvent, you must have a hydrogen bound to oxygen, nitrogen, or fluorine. There is no hydrogen bound to any one of those elements in DMSO. How about methanol? 1. DCM?
2 and 3.
DCM's kind of a weird one. So 2 and 3 isn't a bad statement. Okay, why would we say 2?
Because carbon.
Chlorine to carbon, that is a polar covalent bond. That does generate some polarity. Why are you saying 3? There's 2 chlorines. They are pulling partially against each other. There is still a net dipole pulling that direction, kind of on an angle. Actually, it's just straight up. Okay, why is it just pulling straight up? It's the vector analysis of the 2 chlorines. There is a net dipole that direction. Okay? It just happens to be a very small dipole. Okay? Because of that, it starts to approximate kind of the nonpolar solvent. So dichloromethane, or DCM, sits in kind of a weak polar aprotic system. Okay? Acetic acid is an acid, which means by definition it is protic, okay, or polar protic. Make sense? How do we then use those classifications to help us within our mechanisms? Right, well, we'd have to look at our reactions. If we looked at a substitution reaction, let's see, do I have a prettier slide? Of course not. Surprised I didn't get the embarrassing comment that time. No, it's okay. Let's change the conditions on this to make this an SN2 reaction. What could we do? Based on what we've talked about so far, what could we make it do? Or what could we do to make it an SN2? Strong nucleophile would be great, except I haven't talked about nucleophiles yet officially. We could look at the solvent, but that's what we're trying to establish in the next sequence. Our primary or secondary substrate for an SN2. For an SN1, it would be tertiary. So let's make it primary. and have some letters show up. Why not? So now we are largely suggesting that it is an SN2 reaction because we have a primary substrate, right? If it was an SN2, we would probably also expect a strong nucleophile. And it's strong because it is negatively charged. Because it is negatively charged, what type of bond does it have? Or force. I'll accept force. Let's do force. A negatively charged compound does not have a nonpolar force for a couple of reasons. Nonpolar is not one of our forces, and negative charge doesn't affiliate with nonpolar. Be ionic, right? Because it's an ion. An ion. So we have an ionic force. What kind of solvent are we going to need to stabilize that ionic force so that it can get into solution? It needs to be a polar solvent. Right? So the nonpolar solvent is awful to dissolve it. So we could go up and say, that's what I want. I want either 1 or 2. Okay? Stabilizing the leaving group is kind of a red herring, so let's ignore that one. It's not so much a red herring, but it's easier to look at the other one. What type is going to be bad for a nucleophile? Why is protic bad for a nucleophile? How does it kill it? A protic solvent, whoops. If we take a look at our acetic acid as our typical protic solvent, acetic acid has a very strong what? All sorts of answers to go with that one. Partial positive charge on the hydrogen. A strong partial positive means it needs to be neutralized with an electron source. What was our nucleophile? An electron source. What happens if we use a protic solvent? Stabilizes the nucleophile, and the nucleophile becomes weak. Okay? Well, if we think back to our substitution reactions, where do I care about the nucleophile? In the SN2 reaction, I need a strong nucleophile. So is a protic solvent a good choice for an SN2 mechanism? No, because it kills the nucleophile. What happens if we switch to the SN1? Okay, well, in the SN1, what am I concerned about? A carbocation forming. What do I need to stabilize a carbocation? A negative charge, electrons. Where would I find electrons in my solvents? In a polar solvent, both the polar protic and the polar aprotic supply electrons. Which one supplies more? Protic, because the partial negative charge in our atom will be a larger partial negative because we're looking at hydrogen, oxygen, or fluorine because it's a protic solvent. And hydrogen, or nitrogen, oxygen, and fluorine all happen to be the most electronegative elements on the periodic table. They will generate the largest partial negative. Yes, they generate a large partial positive in the hydrogen, and that will kill the nucleophile. Do I care in the SN1? No. The nucleophile happens at a much later step. I don't care about it. So I can use the solvent to help stabilize and facilitate the SN1 reaction, or I can use the solvent to just not destroy it in the SN2. You are responsible for being able to look at abbreviations for names and know what those solvents are, like DMSO and like DCM. Officially responsible. Okay? I expect you to practice that by the time the final rolls around. If for some reason I use a shorthand like DMSO or DCM and you don't know what it means, raise your hand, I'll draw it on the board. Okay? Nucleophiles are electron donors and or bases. Right? We're going to run into an issue with these. What's the issue between nucleophiles and bases? What do they both do? They both provide electrons. So before we look at the nuances between them, let's take a look through. In bold up at the top in that red box is what you want to focus on. Those are the easier answers to look at. Okay? Number one, they have donatable electrons. Okay? Lone pairs is the biggest one to go for. Pi bonds can potentially work, but in much rarer circumstances. Right? But the lone pairs are primary source of electrons for nucleophiles. Negatively charged nucleophiles are stronger than their neutral counterpart because they're negatively charged. Okay? They're unstable because of that negative charge. And since they can't stabilize that negative, they must seek out some place to dump those electrons. That's where we have electrophiles. So that makes them reactive. Nucleophilicity decreases from left to right. So if we move left to right in the periodic table, what's happening? What's happening to electronegativity? Left to right? It's higher electronegativity. Why would that make it less nucleophilic? It's by definition holding the electrons, not giving them up. Right? The next sequence are harder rankings. Size. Size does play a massive role in nucleophilicity. Unfortunately, the solvent comes in again to kind of bite us on this. The nucleophilicity with respect to size changes depending on which solvent you're in. Okay? So it tends to be such a harder ranking that it's typically not evaluated or tested on. And if you're in a polar protic solvent, the bigger the atom, the more nucleophilic. Okay? If you're an aprotic solvent, the smaller it is, the more nucleophilic. So we're seeing an opposite trend. And then if no solvent is given, the larger the atom it is, the more nucleophilic it is. Okay? Which has to do with this polarizability. Okay? It's large enough that it can give up those electrons pretty quickly. Okay? The last thing is the biggest one, which actually should probably go up higher. Steric hindrance. Where's a nucleophile reacting? With the substrate. Okay, where's a base reacting? Oh, with the substrate, right? Yeah, so defining substrate doesn't help us. So what is the difference between a nucleophile and a base? The depth. The nucleophile has to go deeper into the molecule because what is the nucleophile reacting with? Anything that is not hydrogen. It is typically carbon. Where is carbon found in a molecule? In the center of it, where are the hydrogens? On the outside. Because the nucleophile must get in deeper, it needs to be smaller so that it can get into those tiny spaces. So nucleophiles need to be small. So less atoms affiliated with our nucleophile becomes more nucleophilic. The more atoms affiliated with it, the less nucleophilic it becomes. So our nucleophiles versus solvent. I guess we can look at this. If we take a look at our protic solvent system, what did we say was the stronger nucleophile, larger or smaller? Well, it's cheap. What's it say? Protic solvent. Larger. So if we look at that top example, are we looking at a protic solvent or an aprotic solvent? Protic, hydrogens are typically shown as white, red is oxygen. Why is bromine a better nucleophile than chloride in this system? Bigger doesn't work for this because that doesn't take into consideration the solvent. Because if you say bigger, the bottom one doesn't work.
Because bromide is more stable.
Nope.
The charge on chloride is more concentrated, so it gets more solvated by the...
By having a larger charge or really a higher electronegativity, what happens to the attractive force between the hydrogen of water and our center atom? Becomes stronger. For it to act as a nucleophile, what must it then do? Break that solvent interaction. If there's a stronger force, that's going to be harder to break. So when we're looking at the polar protic solvent, we get a weaker interaction with the bromide in water, which means it can react faster because it doesn't have as strong as an attractive force. Why does it not have as strong an attractive force? It's the electronegativity. What happens when we move to an aprotic solvent? Well, the aprotic solvent, we still have partial positive charges, but those partial positive charges are on carbons, which are located in the middle of the structure, which means we get very weak interactions between our nucleophile and the solvent. Okay? Ultimately weak in both cases. So why does the chloride become a better nucleophile now than the bromide? It's now not the strength of the force, it's the amount. Bromine being larger has more solvent molecules around it, which means I have to remove more solvent for it to react. Okay? Those of you going, wow, that's really tricky. It is. That's why I would just memorize the trend. Okay? Nucleophile versus base. Nucleophiles donate electrons to anything other than hydrogen. That is their definition. Bases, because we're talking specifically about Bronsted-Lowry bases, donate their electrons specifically to hydrogen. Why does sterics play a role? In the SN2, we're doing a backside attack, which means the hydroxide is acting as what? That's not hydroxide. Methoxide is acting as a nucleophile. Are there beta hydrogens? Whoops, let's not attack that one. I don't know where that arrow was starting or going. I lost track of it. What did the methoxide act as now? A base. Are either one of those invalid? No. So it could depend on the question asked. Or I could ask, what is the product of this reaction? Within that context, what's your answer? We could run into a potential SN2 or E2. We'd have to look for some other information to differentiate. What would that information need to be? If we don't look at the negatively charged species, we look at the positively charged. The positively charged species is where? It's the carbon where our leaving group is leaving. What can you tell me about that carbon? It is tertiary. If it is tertiary, what does it have a lot of on the backside? Electrons. What happens if the nucleophile tries to go in? It's repulsed, and what do we end up getting? No nucleophile attack, but the elimination can occur. Right? So when we're looking at these, we're trying to pick the simplest structures and do our fair comparisons. A negatively charged species can act as both a base and a nucleophile. Okay? So let's scale this up. Which of these two would I expect to produce the most substitution? The methoxide or the T-butoxide on the right? Why would the methoxide produce the most substitution? It is smaller. For the other one to get in, what has to happen? It has to get by a whole bunch of electrons, both from the substrate, but also from itself. Which means the structure on the right can't act as a nucleophile. It can only act as a base. So if I want to do an elimination reaction, which of those two bases should I use? The right side, because the right side will primarily give me the elimination because it can only act as a base. If I wanted to do a substitution, then I'd shift to the left side. Okay? And it has to do with the different roles our nucleophiles and bases play. What are they reacting with? This is why definitions are important. Take a look at that structure. What would you expect it to act as? Why a base? I don't see any electrons. It is big, and it's on the nucleophile or base slide, so there's implied lone pairs. Which of those lone pairs is the basic lone pair? The one that's in the middle? I don't know what that means. Top nitrogen, bottom nitrogen. What can the top nitrogen do? Resonance, which does what to its basicity? reduces it, makes it less basic. Can the bottom one do resonance? Nope. Which means the bottom one is our basic atom. Okay. Make sense? Okay. Common nucleophiles. Negatively charged nucleophiles, they've got a list of them. They've got some neutral nucleophiles. Halides are interesting. They can only act as nucleophiles. Kind of small, why can't they act as bases? If they act as a base, what do they become? Not acids. Strong acids. And strong acids, by definition, reverse, get rid of their hydrogens. So our halides will only act as nucleophiles. This is why we typically see them show up in our reactions, because they have very selective chemistry. Hydroxide, not a great nucleophile, because hydroxide is small and can act as both a nucleophile and a base. So we get a mix of chemistry potentially coming out of that nucleophile. Okay. Solvent effects, what the heck? We already talked about this. So if we looked at the SN1, we form a carbocation. Which solvent is better, polar or non-polar, to stabilize the carbocation? Polar because partial charges. Polar subdivides into protic and aprotic. Which is better? Protic because larger partial charges, because the atoms that contribute to the protic solvent are fluorine, oxygen, and nitrogen, the three most electronegative elements. Okay. Let's take a look at these. Acid-base mechanistic extras. So we take a look at this reaction. What's happening in the top one? Substitution. So in substitution, what do we need to have happen? Leaving group. Where's our leaving group? The OH is acting as our leaving group? This is fun. Where do we see the structure with our leaving group? Above the arrow. Does our substrate have to be shown on the left? No, it can be shown above the arrow. Okay, so don't be locked into this, it's always going to mash this way. What do you need to find to decide how a reaction is going to work? A good leaving group. Okay, that's one option. Is hydroxide a good leaving group? No. Is iodide? Yes. So iodide is our leaving group, which then means the structure on the left needs to act as. We compare our reaction. What kind of reaction do we do? Substitution. In a substitution reaction, what are our mechanism types? SN1 or SN2. And that N stands for base, stands for nucleophile. What does our oxygen in this structure need to act as? A nucleophile. So let's go through and have it attack. What do we produce? The structure shown on the far right? Still has the H attached to it. How do we get rid of that hydrogen? Oxygen takes the electrons. What picks up that hydrogen? Oh, we got hydroxide to pick that up. Cool. We now have the product. What is the issue with that mechanism? As a hint, it has to do with that positively charged hydrogen, or oxygen. That structure looks awfully familiar. That's a what? That is a strong acid. What solution are we in? A strong base. Is this mechanism correct? No. Right? We have to be aware of the conditions that we're running the reaction under. I cannot form that intermediate because that intermediate is a strong acid. So what has to happen first? The OH takes the hydrogen from the oxygen first. What do I end up with? negatively charged structure, which could then backside attack and produce the product. So we talked about this briefly when we talked about the leveling effect. Okay? You cannot form positive charges in a basic environment because basic environments are inherently negative. Don't make positive charge. Okay? What's happening in the bottom one? Kind of reaction. Substitution. Right, we've got a choice of nucleophiles here. We could do that. What do we get as a substrate? Whoops. Everybody agree? That's a positive charge in an acidic environment. Is that a problem? What was the leaving group? OH what? What did I just form? A strong base in a strongly acidic environment. Watch for your leaving groups. Watch for those extra pieces. Make sure that we don't start forming those strong acids or bases in those environments. Okay. With that, the intramolecular, bad versus good, we'll come back to and talk about in Unit 3. We'll look at our alkyne chemistry, primarily our elimination and substitution in Unit 3. Okay, there's more of our intramolecular. Come on, slides, work with me. But here's what I was really trying to get for. Okay. This slide summarizes our mechanism for the SN1. You're responsible for all aspects of it. Okay. This one shows it slightly simplified, but it also lists all of the pieces necessary for an SN1. Substrate, leaving group, nucleophile, all of those things, okay, which were intended to be stepwise through nice and slowly, but they aren't going to be. Okay. Substrate, we need to form a stable carbocation. Leaving group needs to be good. Nucleophiles, weak or irrelevant. Solvent, polar, protic, stereochemistry, we lose it. Complications, rearrangements are possible. Everything we just talked about is now summarized on one slide. SN2, we've got the mechanism. We've got our rate law, backside attack, steric hindrance, all of our key words. What do we need for the substrate? Smaller, better. Okay. All of the key things nailed down on one slide. Okay. So if we're trying to decide between substitution, our SN1 or our SN2, we can evaluate side-by-side comparisons. We can do the same thing for our E1 mechanism, all of the pieces. Okay. We can do the same thing for the E2, all of the pieces. Okay. There's a nice chart that puts it all together again, so we can now compare each of those pieces all the way through. Okay. The big outcome of all of Chapter 9 is this table that the textbook gives you, which is pretty useless, so we modified it into this guy. You now evaluate the nucleophile for SN1 and SN2. Okay? Based off of our discussion of SN1 and SN2, we know that the SN2 needs to be strong. So if I have a strong nucleophile, check mark. Weak nucleophile, check mark in the SN1. I would go through and evaluate each of those pieces, total them up, and see what I get. Whichever one has the most points wins. That's the mechanism you need to do. Do you have a tie? Guess what you need to do? All the products. Okay? Every single one of them comes out evenly. It won't happen, but let's say it did. You would have 4 products. Okay? This is another version of how you can organize it stepwise, the thought process that you should be thinking about. Look at your strength. If it's strong, it's bimolecular. Doesn't matter if it's E2 or SN2. Once you've established it's strong, then decide, is it a nucleophile or a base? Okay. Then you can move to substrate structure. How does the substrate structure stack out? Okay. Then you can move to the solvent. Then you can look at temperature. These are all things of helping you organize and process your way through each of those steps. And with that, we end up with a black screen because we're done.